Hello everyone. So today we're going to start on 13.2. So 13.2 is called Matrix Exponentials. So clearly from the title it involves matrix and exponential. So let's see how this goes. Okay. So let's start by remind you something first. Oops. Recall. Let's say we have an equation dy over dt is equal to ay. We know that it has an exponential solution. Mainly this y equal to e to ax will, well actually I can put a constant in front, y equal to c e to ax will satisfy this equation. Mainly one of the reason is because exponential function is one of these weird functions that when you take the derivative, it actually get back to itself, which basically allow us to see that this is basically what this equation tell me is that you're looking for a function where when you take the derivative, it's just equal to a multiple of itself. An exponential function does that because the exponential function, when you differentiate, it can't just go back to itself repeatedly. So now come the question. So now consider a system of differential equations in the form of of course I forgot. Here a has to be a constant. Okay, so in the form of d vector x over dt equal to a vector x with a constant matrix A. So notice that this equation written very similar to the equation that we have on top, except that I changed the y to vector x, and because of that our A, which is a scalar, now become a constant matrix A. Would it be nice if we can find an exponential solution for this equation also? So here comes the question. Is it possible to find an exponential function, an exponential solution, similar to dy over dt equal to ay? So obviously the best case scenario is for us to have a solution where the solution is just e to the matrix A t. Oh, actually, you know what? I wrote x. It should be t right here. There you go. That would be great. But then the problem is we have a matrix in place of a scalar. So see, it makes sense when I say e to the at, where a is a scalar. That makes sense because we know how to define that. But if I now want something similar, but I have a matrix, a constant matrix A, surely we can't really raise e to a matrix power, can we? Well, as it turned out, we can. We just need to learn how to define it properly. So, here's how we go define this concept of raising a e to an exponent that is a matrix. In BC calculus, you have learned that we can define an exponential function using a power series. As a matter of fact, the definition of an exponential function can be defined to be e to x is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot 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 plus x to the n over n factorial plus dot dot dot. And so we can think of it as an infinite summation. Like that. Or sometimes I write it this way. Actually, you know what? I don't want to use n because I might want to use n as a top number, like n term. So maybe I use a different index. J. So that's how we define an exponential function not using exponential function or exponent, but rather define it as a power series, or more accurately, this is probably referred to as a Maclaurin series or Taylor series. Okay. So is it possible for us to actually input a matrix into A? Well, if you remember learning it back in multivariable calculus last year, notice that matrix multiplication is not commutative and is also not closed. But for a very specific type of matrix, it is closed, and therefore allow us to repeatedly doing that, and that is a square matrix. So let's say we let A be an n by n square matrix. And let's say we're going to let I be the identity matrix for whatever dimension we need. So most likely in here we need an n by n. Then we'll define something called matrix exponential to be the following. And we'll define the matrix exponential to be given by this formula. We're going to call that e to the matrix A. And that will be given to be I, which is the identity matrix, plus matrix A, plus A squared over 2 factorial, plus A to the third over 3 factorial, plus dot dot dot, plus A to the n over n factorial, plus dot dot dot. And therefore forming this summation. Or we can write it like this by separating the coefficient and the matrix. So that is what we're going to be defined as called matrix exponential, which is basically taking the power series of the e to the x and putting A in place of x. And this matrix exponential also can have a different notation. A different notation for e to the a is called expa. So when you see that basically means the same thing. In a sense, some cases it makes sense to do expa because it is slightly different than like raising a to power. Because in here, when you say e to the x, or like let's say e to 2, you can interpret it as e times e twice. But you raise e to a matrix power, there's no such interpretation as to how many times I multiply e to form this. You actually can't. So that's the reason why there's a separate notation for it to kind of indicate that it's not kind of the same thing as e to the a. E raised to a scalar power. But it does have several important properties that make it similar to what e to the numerical or e to a scalar power is going to be. Now, how do we actually form this, and what does this e to a actually come out to be? Well, the interesting thing about it is the following. Note. if A is n by n matrix, then shockingly, e to a is also an n by n matrix. Students often don't realize that. No, you don't come out some kind of scalar. The reason why, because if you think about it, the way it's defined, if A is an n by n matrix, then obviously here A will be an n by n matrix, and since square matrix raised to a power is closed, that means a squared, a to the third, a to the fourth, a to the fifth, and so on and so forth are all n by n matrix. And they simply have a coefficient multiplied to it. So essentially, when you look at this summation right here, it's simply just adding a whole bunch of, as much as infinitely many, n by n matrix together. And since matrix addition is closed, therefore it will result in an n by n matrix. Now, maybe it's hard to understand or wrap your mind around how this e to the a works, so maybe we can give a very simple, concrete example. Now, before we actually look at this example, I do want to point out, this is a very simple example. It's by design, so not all matrix exponential work out to be as simple as this one. Okay, as a matter of fact, we will be spending majority of chapter 13.2 learning how to find this matrix exponential, because it helps us identify the solution to a system of differential equation. But let's start with a very basic example. Let's say we're going to let matrix A equal to this diagonal matrix. So diagonal matrix are particularly nice and easy to work with. As a matter of fact, if you pursue more into linear algebra, you will actually learn how to manipulate a matrix into a diagonal matrix, and then how to use it to solve problem. And of course, the tricky part here is to understand that when you manipulate the matrix, it changes some of the other aspect of it. And the key is to learn how to keep track of those, and then when you use it to solve the problem, you can account for those changes. So, but unfortunately, that's not part of what we're going to do. But regardless, we're going to use this simple diagonal matrix, and we're going to try to find what is e to a going to be. All right, so ready? So, well, let's start by the definition. So, e to a is just equal to I plus a squared over 2 factorial plus a to the third over 3 factorial plus dot 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 plus a to the n over n factorial plus dot dot dot. And obviously, it's not practical for us to try to actually evaluate this sum because they're infinite terms. So what we're going to do, well, one, we could estimate by ending this sum at some point, but that obviously not going to give us the best answers. So how should we approach this? Well, the way to approach this is to actually learn that we don't sometimes have to evaluate infinite sum by adding infinite terms. We can somehow use our mathematical knowledge to come up with an idea to see what this sum actually converges to. So how do we do that? Well, how about let's start by just try to figure out what are some of these power of a going to look like first, and maybe there is some kind of pattern that we can use. So I'm going to go and start. So a to 0 obviously is 1, 0, 0, 1. So that's pretty simple. A to first is clearly 2, 0, 0, 3. So now the question comes down to what is a squared going to be? Well, that would be 2, 0, 0, 3 times 2, 0, 0, 3. And what's the nice thing about diagonal matrix is that when I do that, I actually just get 2 squared, 0, 0, 3 squared. And now let's do a to the third. So that would be a squared multiplied by a again. And that actually comes out to be 2 to the third, 0, 0, 3 to the third. Now, I'm hoping everyone see a pattern here. If I continue this process and try to identify what is a to the j, that would probably give me 2 to the j, 0, 0, 3 to the j. That's a pattern that we can now use. So now let's try to figure out what is e to the a. So e to a would basically equal to 1, 0, 0, 1 plus 2, 0, 0, 3, plus 1 over 2 factorial, 2 square, 0, 0, 3 square, plus dot, dot, dot. And I'm going to go and write out in summation form too. Summation j from 0 to infinity, 1 over j factorial, multiplied by 2 to the j power, 0, 0, 3 to the j power. So now it's just a matter of trying to figure out what the summation is going to be. And it's actually not too bad to do, because even though we have a summation of a matrix, but nice thing about it is that because the summation property is technically speaking linear. So what I can actually do is this, is to actually move the summation inside our matrix. By simply apply that same summation to all the entry inside. And clearly, these two things are just going to go to 0 because I'm basically summing up infinite 0. So that's nice. So now the question comes down to, what are the other two things going to come out to be? And some of you might have a little deja vu, because if you look at that, that's technically look just like this thing right here. What's the difference between this thing right here compared to what we have? Is that this thing has an x to the j, we have a 2 to the j. And if you look at what's equal to, that's equal to e to the x. So therefore, if I look at this correctly, I replace the x with the 2 in this summation. Therefore, I should basically replace the x in e to x with a 2 also. And that's exactly what it's going to be. So this actually just come out to be e to the second, 0, 0, e to the third. So this thing right here is basically what we call e to the a, or you can write it as exp a, which is basically exp 2003. It's kind of weird to write a matrix as the exponent for e, which is the reason why the exp notation is created. So they actually look kind of nice in that way. But that's what our answer is, right here. Now, of course, as I say, this is a very simple example. No, not all matrix, when I put in e to the power, it will just become e to whatever number inside the matrix. That's not how it's always worked. It's just that for the diagonal matrix, it does work out to be like that, and that is a special property of a diagonal matrix, which is one of the reasons why we like to work with diagonal matrix. If you think about it, you actually have encountered diagonal matrix before already. The lambda sub t matrix from before is a diagonal matrix. So, now that we have an idea as to what matrix exponential is, before we actually get into more of how to find it, because that will be one of the difficult things that we have to do, is to try to figure out how to actually find the diagonal, find the matrix exponential for a given matrix A. So, but before we do that, let's establish some properties about this matrix exponential that we can exploit. And of course, the key thing about it is the following. Is one of the reasons why we write matrix exponential e to the a, because we want to think of it as like the exponential function that we already know from real numbers. Mainly because there are a lot of properties about this matrix exponential that actually exactly work out the same as our basic e to the x function. So show you. Here's theorem 13.2.1. We're going to try to prove some of these properties, but of course, we probably not going to be able to do all of them today in today's video because we're only 20 minutes into the video already. So here's what the theorem say. If matrix A is an n by n matrix, constant matrix, and it doesn't matter whether it's real or complex. So even if entries inside a complex number, it still work. Then we know that then the matrix series basically mean an infinite sum of the following matrix in the form of summation j from 0 to infinity t to the j over j factorial a to the j will convert no s to an n by n matrix called e to the ta that satisfy the following three properties. Okay, so this first thing is say that if you have a square matrix, it will always convert when you form this summation. And whatever this summation add up to, we're going to give that a name and call it e to the ta, which is the matrix exponential. The t is basically what the variable is, and then a is basically what the coefficient matrix is. Okay, and in this case, I can put t times a because t is a scalar, so it can be multiplied in front or after. You could write this as e to a t if you want. I just like to put t a, just look nicer, but I can definitely see being at is better because it kind of look like this right here, except I changed the a to capital A. So really up to you. As a matter of fact, you might see me sometime write as at, sometime write ta. Okay. So what are the three properties that it has to satisfy? Number one, and we're going to prove each of these, but I'm going to state all three of them first. The first one is the following. If you have e to the t plus s times a, that is actually the same as e to ta times e to the sa, which is also the same as e to sa times e to ta. For whatever scalar s and t. So notice that this basically tells me that if I multiply two matrix exponential together, I can simply just add their exponent together, which is exactly how e to the x work, or well, not just e to x, but any exponential function work. Is that when you multiply two things that have the same base but with different exponent, you just simply add the exponent together. And also another very interesting thing that this property allows us to state is that when you're doing this, it is actually commutative. E to ta times e to sa is the same as e to sa times e to ta. So that's actually pretty interesting. Two, if e to ta is always invertible, and we can define the inverse of that to be negative e to negative ta. So if you take e to negative ta times e to ta, you would get the same thing as e to ta multiplied by e to negative ta, and they both give you I. All right. So that's pretty interesting. And once again, I have to state the property in both reverse order. The reason is because matrix multiplication is not commutative. So we actually don't know. I cannot assume that the matrix multiplication work the other way would be the same. notice that this property is also work out exactly the same way as e to a scalar, meaning like e to 2 and e to negative 2 are inverse of each other, and when you multiply them together you get the identity, which is the number 1. So notice that even though you might not think that this matrix exponential, I mean, it's not the exponential function because you're not technically saying e raised to some power, but yet when you define it using the power series, it actually follows some of the properties that we already established with exponent, which is extremely interesting. But both of these properties definitely allow us to manipulate the expression, and it makes sense because it kind of follow what the exponential rules are. But it is this last property that we're going to talk about that is probably the most important for us, and that's property number 3, which states the following. If you take e to the ta and you take the derivative of that with respect to t, guess what we get? We actually have a e to ta, or e to ta times a, depending on which way you want to write the multiplication. And in this case, once again, the multiplication is commutative, so therefore it doesn't matter which way you write it. And remember, that's not generally true with matrix multiplication. Okay? So that's how that the e to ta or e to at work out, is that they actually follow the same property as exponent rule, where you can multiply, you add the exponent together. When you form the inverse, you put a negative. Now, however, we don't have 1 over e to ta, so don't think of it that way, as the negative exponent doesn't make it into like 1 over, because we don't know how to divide matrices. So keep that in mind. That's not the case. Okay, the here e to negative ta simply just be the inverse of e to ta. Okay, a multiplicative inverse of it, but not necessarily as a reciprocal like real number would do. Okay. And probably the most important thing is that when we take the derivative, it actually follows the same rule as the derivative for e to the scalar at. Because when you do that, it just forms the number in front. So this actually mirrors the rule for therefore imply, probably the most important thing that that probably the last thing we're going to talk about, is that imply that when we take the derivative of a matrix exponential, it actually winds up being some kind of matrix exponential of itself. Same exact property as e to the t. When I differentiate, it becomes e to the t. And then when you differentiate e to at, it becomes some multiple of e to at. Here, when I differentiate e to the t matrix exponential e to ta, it forms some kind of multiple of the matrix exponential e to ta. So that actually worked out perfectly for us to try to use it to form the solution to a system of differential equation. Now, unfortunately, I'm going to stop right here. It's 28 minutes in, and I don't want to get into one of these proofs because it will take a while to do. So I'm going to go and stop right here. So tomorrow's video, or the next video, we will prove some of these properties. And then we're going to try to learn how to use that to our advantage in solving system of differential equation. All right. Okay. That's it for today, for this video, and I'll talk to you guys really soon. Okay. Bye-bye.